Hello, my name is Birendra Yadav. I am a B.Tech graduate from IIT Roorkee and I train students for IIT JEE exam. Today I want to discuss few important concepts of solid state. Many times I found that students ignore this chapter during their preparation of IIT JEE exam. But if we analyze previous year's IIT JEE papers, we can find that every year at least one question is asked from this chapter. In fact, in 2008, a passage of 12 marks was based upon solid state. Here basically I want to discuss different types of questions that can be framed with the help of the concepts of solid state. Few important concepts of this chapter are like close packing of spheres, packing fraction, especially in HCP, concepts of voids and radius ratio, and concepts of ionic solids and defects. Here I am going to discuss different types of questions that can be framed with the help of concepts of solid state. Consider this question. This question says marbles of radius 5 mm are to be placed in a square area of side 40 mm such that their centers are within this area. What will be the arrangements of marbles on a plane so that maximum number of marbles can be placed inside this area? In fact, similar type of question was there in IIT JEE Mains 2003 exam. Now to deal with these types of questions, we need to know close packing of spheres, the concept of close packing of spheres. If we try to place spheres closely on a plane, the two possible arrangements are there. One is like this. This is called square close packing. Another arrangement is like this. This is called hexagonal close packing. If we compare the two, here one sphere is in contact with 4 spheres, while in this case one sphere is in contact with 6 spheres. The packing in this case is better than square close packing. So from the packing point of view, we can say this is more economical. Now if we extend this structure three-dimensionally, two close packings have been observed. One is called as AB type of packing. Alternatively, it is called as HCP, hexagonal closed packing, and the other is ABC packing. Alternatively, it is called as CCP, cubic closed packing. In both the cases, the packing is approximately 74%. Now if we look at this question, in this question we need to put maximum number of marbles within the given area. So obviously we have to take this second arrangement to get maximum number of marbles in a particular area. since the side length of this square is 40 millimeter, so this side will go like this: 5 plus 10 15, 10 25, 10 35, and 5 40. So by this way 40 millimeter. Here also we need to get 40 millimeter. To get the actual length, we'll draw this structure. Let this as P, Q, R, this N. We need to get this length X. This is 10 millimeter, 10 millimeter, 10 millimeter. So this is an equilateral triangle. So each angle will be 60 degree here. P, Q, R, and we need to get this length X. So here we can use sin 60 is equal to X by 10. So X will be 10 sin 60 is root 3 by 2, which will be 5 root 3 millimeter. We'll extend this X, 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 X. So if we try to find 4x, it will be 4 into 5 root 3. So 20 into 1.732, which will be equal to 34.64 millimeter. If we add 5 millimeter more to this, the total length will become 34.64 plus 5, which is approximately 40 millimeters. So by this way we draw this side. Now we need to find effective number of atoms within this square. So try to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 spheres are completely inside this area. If we look at this sphere, this sphere, this sphere, this one, this one, this one, and this one. 1, 2, 3, 4, 5, 6, 7. These 7 spheres contribute only half to this particular area. So effective number of spheres will be 7 by 2. Now if we look at this sphere and this one, these two spheres contribute only 1 by 4 to this particular area. So contribution will be 1 by 4. So I can write 2 by 4. By this way I get 14 plus, and here I get 4. So 18. So I can say 18 spheres can be placed within this area. So we can say to get effective number of marbles, maximum number of marbles, basically we need to pack spheres closely on a plate. So this is the correct way. Many times exams like IIT JEE, they ask questions from packing fraction, especially in HCP. In 2008 IIT JEE exam, there was a passage of 12 marks based upon this HCP, hexagonal closed packing. Now to get the packing fraction in any unit cell, we need to draw that unit cell. Here, first of all, we need to draw HCP unit cell. The structure is like this. There are 12 corner atoms here, 2 face center atoms, and 3 atoms are inside this body. If we join these 2 atoms, the line passes through centroid of this triangle. In the first layer, these atoms are touching each other. So we can say, if this length has A, we can write A is equal to 2R, where R is the radius of this atom. Let this as C. The height is C. Now, first of all, what is packing fraction? Packing fraction is basically fraction of total volume occupied by sphere. Packing fraction can also be written as effective number of atoms into volume of one atom upon volume of unit cell. We can say atoms are taken as spheres, so volume of one atom can be written as 4 by 3 pi r cube. Effective number of atoms, let this as Z. Volume of unit cell. This is the hexagonal closed packed structure. Volume of this unit cell will be area of the base into height. So area of base into height. Now how will we find the area of the base? For this, we will divide this regular hexagon into 6 equilateral triangles, each side A. So this can be written as Z into 4 by 3 pi r cube upon area of the base will be 6 into area of one equilateral triangle. So area of the equilateral triangle will be root 3 by 4 and the side is A, so it will be A square into height here is C. So this is the final packing fraction formula for HCP. Here we can be asked to calculate the relation between A and C. We can be asked to find the volume of the unit cell. So different types of questions can be framed if using the concept of HCP. So we'll discuss these things in detail. First of all, we'll discuss here effective number of atoms. How to find effective number of atoms in this case. To get effective number of atoms, we need to know contribution of these atoms to this particular unit cell. Consider this corner atom. The corner atom is like this. Since this angle is 120, so we can say 3 unit cells can be placed on one plane. So this corner is surrounded by 3 unit cells on one plane. and 3 will be above this plane. That is why overall this corner atom is surrounded by 6 unit cells. So contribution to a particular unit cell will be 1 by 6. Now total number of corner atoms here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 corner atoms, contribution is 1 by 6. So effective number of atoms from the corner will be this. Plus, these two are the phase center atoms. As we know, the contribution of phase center atom to a particular unit cell is 1 by 2. So effective number of atoms here 2 into 1 by 2. These 3 atoms are within this body, that is why contribution will be 100%, 3 into 1. So by this way, effective number of atoms 6. So 6 is the effective number of atoms. Now next we need to get the relation between A and C. As we know, this is the second layer, this is the third layer. So obviously this atom will touch these 3 atoms. If this atom touches these 3 atoms, so this length will be 2r, 2r and 2r. And since these 3 atoms are on one plane, so these 3 atoms also touching each other, so it will be 2r, 2r, 2r. As we know, A is equal to 2r. If I say this as P, Q, R, M, and we draw here, so it will be like this. Each length as A, and we have assumed this as P, Q, R, M. Now this is the equilateral triangle. If we join this with the midpoint of QM, let this as N. So obviously this length will be A by 2 perpendicular. So this is A, this is A by 2. We can get the length Rn. Rn will be root A square minus A square by 4. So it will be root 3 by 2A. Root 3 by 2A. Now if we draw a perpendicular from point P like this, let this point as O. So basically this line passes through the centroid of this triangle, so we can say this perpendicular will cut this Rn line as 2:1. Now since this is 2:1, we can get the length RO. It will be 2 by 3 of this total, 2 by 3 of Rn. So it will be basically A by root 3. Now substitute here, we get this A by root 3. Now if we take out this triangle P, O, R, this as perpendicular, OR we know as A by root 3, PO is basically half of this total length, so it will be C by 2, and PR, this is A. So we can use Pythagoras theorem here. So I can write A square is equal to C square by 4 plus A square by 3. So I can get the relation between C and A in this manner. So I can write here c square by 4 is equal to a square minus a square by 3. It will be 2a square by 3. So here c square can be written as 8a square by 3. So the value of c will be 2 root 2 by root 3a. So here you can see this is a relation between c and a. Now to get the packing fraction, we will substitute this relation in that formula which we have written earlier. So the packing fraction will be, as we know, effective number of atoms is 6 into volume of one atom was 4 by 3 pi r cube upon 6 into volume of unit cell was 6 into root 3 by 4 a square into c. C value is this 2 root 2 by root 3 a. So it will become 6 into 4 by 3 pi. As we know 2r is equal to a, so the value of r in terms of a will be a by 2, so I can write a cube by 8 upon 6 into root 3 by 4 into 2 root 2 by root 3 a cube. This a cube will get cancelled, 6 cancelled, so effectively it will be 4 into pi into 4 root 3 upon 3 root 3 into 2 root 2. Now if we calculate this, the value comes out to 0.74. So packing fraction in HCP is 0.74 and percentage packing will be 74%. And keep in mind, if we are asked to calculate the volume of the unit cell, so this will be the volume of the unit cell, HCP unit cell. Now I will take another question. The question says an element crystallizes in FCC lattice having edge length of 400 picometer. Calculate the maximum diameter of atom which can be placed in interstitial site without distorting the structure. Actually the question is of IIT JEE 2005 exam. Now to deal with these types of questions, we need to know the concept of void and radius ratio. Consider FCC unit cell. FCC unit cell can be drawn in this manner. Here atoms are at corners of the cube as well as face centers. Of this unit cell. This FCC unit cell has two types of void. One is tetrahedral void and the other is octahedral void. Now what is tetrahedral void? If we place 4 atoms in this manner, like this, then the void or gap between these 4 atoms is called tetrahedral void. Now why do we call this as tetrahedral void? If you join the centers of these 4 atoms, we get a tetrahedron. That is why we call this void as tetrahedral void. Now what is octahedral void? If we place 6 atoms in this manner, the void here between these 6 atoms is called octahedral void. Now why do we call this as octahedral void? If you join the centers of these 6 atoms, we get an octahedron. That is why the void is called as octahedral void. Now to deal with these types of questions, we need to know the size of the atom which can be placed inside this tetrahedral void or octahedral void. First we will discuss tetrahedral void. Now if we want to place atom inside this tetrahedral void, we can draw in this manner. Keep in mind, these atoms are touching each other. So let the radius of this atom as R. This is the void where we have placed another atom. This distance can be written as 2R. Let the radius of this atom which is placed inside the void as small r. As we know, this angle in case of tetrahedron, it will be 109 degree 28 minutes. So half of this angle will be 109 degree 28 minutes by 2 is equal to, it will be 54 degree and then 44 minutes. This length will be small r plus capital R. Now this triangle, we can use here sine 54 degree 44 minutes. I can write as sine 54 degree 44 minutes is equal to this length as r upon small r plus capital R, and the value of sine 54 degree 44 minutes is 0.816. Now from here, if you want to find small r upon capital R, this comes approximately 0.225. So this will helps us in finding the size of the atom which can be placed inside the tetrahedral void. Now we'll try to find out the size of the atom which can be placed inside the octahedral void. Now in case of octahedral void, we have to draw this and the inside the void we put another atom. If we take a cross-sectional view, we can draw in this manner, like this. Let the radius in this case as r. Let the size of the atom which is placed inside this octahedral void, let the radius as small r. So if I draw this, I can say this angle as 45 degree. This is basically a square. So I can use here cos 45 degree, which can be written as R upon R plus R. From here, if I try to find R plus R upon R, it will be root 2 basically. Root 2, that is 1.414. So from here I get R upon R as 0.414. So this will help us in finding the size of the atom which can be placed inside the octahedral void. Now if we look at the question says you need to find the maximum diameter of the atom which can be placed inside the void. Now if we compare the tetrahedral void and octahedral void by looking at the radius ratio, in case of tetrahedral void the radius ratio comes 0.225, and in case of octahedral void the radius ratio comes 0.414. So obviously to get the maximum diameter we need to take octahedral void, and that is why radius ratio will be this. So in FCC unit cell, if you want to put the atom with maximum diameter inside the void, we need to consider octahedral void, and that is why we can write small r upon capital R as 0.414. Second, these atoms are touching each other. In FCC unit cell basically atoms, this face center atom will touch these corner atoms. So I can say this as R, 2R, R. So 4R can be written as A root 2. This length will be A root 2. Since A is given as 400 picometer, so I can write this as 400 root 2. And from this we get the value of R, and I can substitute this value here. So I can write this as small r is equal to capital R into 0.414, and this capital R is nothing but 100 root 2 into 0.414 picometer. Since we need to get the diameter, so that is why we have to take 2R. So diameter of the atom which can be placed in the octahedral void will be 2R. It will be 2 into root 2 into 0.414 into 100. If we solve this, we get approximately 117 picometer. Another question that I'll take here is the crystal XY, which has rock salt structure, has molecular weight 6.023A. Further, the question says if the minimum distance between cation and anion is 8 to the power 1 by 3 nanometer and the observed density is 20 kilogram meter cube, find the type of defect. Now, to deal with these types of questions, we need to know the concepts of ionic solids and defects. Different ionic solids that we need to study are NaCl type structure, ZnS type structure, CaCl type structure, CaF2 fluoride structure, Na2O antifluoride, etc. Here I am going to discuss NaCl type structure. Basically we need to know features of these structures. two important features of NaCl type structure are, number one, the anion, Cl minus for example. Anions are arranged in a CCP manner. And cations are there in octahedral void. Now on the basis of these two features, we can conclude certain points like since anions are in CCP manner, so effective number of anions will be 4. Effective number of anions will be 4, and since the ratio is 1:1, that is why effective number of cations is also 4. On this basis, we can say one unit cell of NaCl has 4 NaCl units. A very important conclusion. One unit cell of NaCl has 4 NaCl units. Now, by looking at the second feature, since it says cations are there inside the octahedral void, which means the coordination number of cation is 6. And since the ratio is 1:1, that is why coordination number of anion will also be 6. Now if we draw NaCl structure, anions means Cl minus at corners of the cube as well as at facing, and the cations are inside the octahedral voids. As we know, octahedral voids are there at body center and edge center. So this will be the structure of NaCl solid. As you see, this cation and here the two anions, this distance is A. Since the cation touches these two anions, so we can say like this, it will be R minus, and here 2R plus. So I can write 2R plus 2R minus is equal to A, means R plus R minus is equal to A by 2. So I can say the minimum distance between cation and anion in NaCl type structure is A by 2, where A is the side length. Now I will discuss different types of defects that are found in ionic solids. Different defects that we need to know here are like Schottky defect, Frankel defect, metal excess defect, metal deficiency defect. These defects we need to study in detail. Here I wanted to tell you that in Schottky defect we can say pair of ions missing. In Frankel defect a cation moves into interstitial site. Schottky defect are found in those ionic solids where cations and anions do not differ much in size, while in Frankel defect the size of cation is much smaller than the size of anion. In Schottky defect density decreases while Frankel defect density remains same. In metal excess defect, as you see here, the density increases because metal is in excess. Now if density increases, then observed density will be more than calculated density, while in this Schottky defect the observed density will be less than the calculated density. Now look at the question. The question says you need to find the type of defect. Here observed density is given, which means we have to calculate the density on the basis of given data. Here as you see, the XY structure is basically rock salt structure. Rock salt structure means NaCl type of structure. In NaCl type structure, one unit cell has 4 units of XY. 4 units of XY. Now, how to find density? Density is nothing but mass by volume. Mass of the unit cell, volume of the unit cell. Now how will you find mass of the unit cell? Since one unit cell has 4 XY molecules, so mass of one unit cell will be 4 into mass of XY molecule upon volume of the unit cell. Let the length of the unit cell as L, then volume will be L cube. As we know, in NaCl type structure, the minimum distance between cation and anion is L by 2, and here it is given as A to the power 1 by 2. So I can say L by 2 is equal to A to the power 1 by 3, which means L is equal to 2 into A to the power 1 by 3. Now substitute all the values. 4 into, to find the mass of one XY molecule, I will write molar mass of XY molecule, which is given as 6.023 A divided by 6.023 into 10 to the power 23 into volume is L cube. So I will put here this 2 A to the power 1 by 3, which will become A. Now if I calculate, but here keep in mind this A to the power 1 by 3 is given in nanometer. So L will be in nanometer, and since we need to find this in kilogram per meter cube, so I will convert this nanometer into meter. So I need to put 10 to the power minus 9 cube, and since mass in gram and we want in kg, that is why we need to put 10 to the power minus 3. Finally it will become 1 by 2 into 10 to the power minus 23 will become 26 upon 10 to the power minus 27. So it becomes 10 by 2, which is 5 kilogram per meter cube. As you see, the calculated density is 5 kilogram per meter cube, while the observed density is 20 kilogram per meter cube. So we can say the calculated density is less than the observed density, and that is why the defect will be metal excess defect.